Good evening, everyone. Good evening. Good evening. I welcome you all again to the JEE Enthuse. Well, people, if I'm audible and visible to everyone, hit the chat box with a thumbs up. Let me know if I'm audible and visible to everyone. Hi, Abid. Hi, Nishant. Hi, Sahana. Hi, Saurabh. Hi, Kirito. What's up? How are you guys doing? Good evening. Good evening, everyone. Good evening. Hope all of you are doing great, having the good time. Hi, Anisha. Good evening. Hi, Bhargav. I'm doing wonderful. How are you? How are you guys doing? I'm doing great. I'm doing great. I'm doing great. Yes. Kirito, I'm doing wonderful. How are you doing? That's wonderful. Hi, Asit Kumar. Welcome to the session. Hi, Mir Mariam. Walaikum Salam. Welcome to the session. Welcome to the session. So, how are you guys doing? Let me know in the chat box. Let me know in the chat box if you guys are doing great. Yeah? Hi, Akash. Anisha, I'm doing great. I'm doing great. Hi, Navneet. Good evening. Hi, Rishabh. Good evening. Hi, Anisha. Hi, Sirkali. Good evening. Oh, Josh is hi. That's wonderful. That's wonderful. Yeah? Okay. So, people, as you all must be knowing, in the last session, we talked about the adiabatic processes in detail. Yes. And in the today's session, we are again going to talk about one of the important process, which is what we call as polytropic process. Okay. Today, I'll be telling you what polytropic process is all about. How do we calculate work in polytropic processes, and how do we calculate the molar heat capacity? Yes, all these things I would discuss in the today's session. Yes. Okay, good evening, cool girl. Good evening, good evening, good evening. Welcome to the session. Just a second, guys. Yeah. Okay. All right. So before starting the session, as I always say, my name is Wassim Sir and I'm your chemistry master teacher over here, as you all must be knowing now. Yeah. Let me show you the schedule of the week, guys, which I show almost in every session, right? Yeah. We are done with the reversible, irreversible processes. We are done with the isothermal process. We are done with the adiabatic process. And today we are going to talk about the polytropic process. Tomorrow we'll be talking about the free expansion and the cyclic process. And on Saturday, we'll be talking about the entropy of the system, entropy of the surroundings, entropy of the universe. Yeah? Okay. So this is the Mega Menti Sprint series, as you all must be knowing. Yes. Exactly, guys. On Tuesdays, you have got the Menti quiz with the Shmon Sir. On Thursdays, you have got it with the Shreyas Sir. Okay. On Saturdays, you have got the Menti quiz with me at 1 p.m. sharp. Okay. And in the coming Saturday, I'll be doing it on electrochemistry. We'll be having the Menti session on electrochemistry, right? So stay prepared and do not miss this session at all. Correct? Okay. Anisha, I have not started organic yet. Organic will be started soon, so you do not worry about that. Now, NEET Elite session, it didn't get postponed. I have shifted the slot. Today, I'll be taking the night session at 11 p.m. Yeah, from 11 to 12, I'll be taking the session on NEET Elite. Yeah, let's see how it goes. Let's see how it goes. It's the experiment. Yeah. Okay, so people, do like, share, and subscribe the channel so that everyone will get benefited out of it, as I always say. Yeah. Okay, so before starting the session, let me give you the brief introduction about the Vedantu JEE Pro subscription, what all benefits you guys are going to get if you'll enroll yourself in the Pro subscriptions. If you're getting the Pro subscription, what all benefits you guys are going to get. Yeah, the first thing, guys, that is important, you're going to get the 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5+ years of experience will be helping you out personally for your upcoming JEE 2021 as well as JEE 2022. And you have got complete liberty to learn in English as well as Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu personally. Yeah. Yes, Fida, it's at night 11 p.m. Yes, absolutely. Okay, and people, let me tell you, we are going to cover everything which includes your micro as well as crash courses over here in this Pro subscription. Now, for the people who are going to appear in the JEE in 2021, we have come up with 3 different plans, as you all can see. The first plan, which is the 1-month plan, after the 20% off, you guys are just getting it for 6K. 3-month plan 16.8K, 6-month plan 31.2K, and on every plan you have got 20% off right here. And all these plans are valid for the ones who are going to appear in the JEE in 2021. Yes. Now people, for the ones who are going to appear in the JEE in 2022, we have come up with 4 different plans for you as well. Let me show you the first plan, which is the 1-month plan. After the 20% off, you guys are just getting it for 4K. 3-month plan 10.8K, 6-month plan 19.2K, and 12-month plan after the 20% off, you guys are just getting it for 33.6K, correct? And all these plans are valid for the ones who are going to appear in the JEE in 2022. And for the droppers, 3 plans we have. On every plan, we have got 20% off again. Yes, 1-month plan after the discount 7.2K, 3-month plan 20.4K, 6-month plan after the 20% off, you guys are just getting it for 40.8K. Now the point is, how do we get these plans? Let me tell you, there is one link in your description box. Go to the description of the video, just click on the link which is there, right? Use the coupon code as WBPRO. After using this coupon code of WBPRO, you guys are going to get the discount of 20% on whatever plan you're selecting for yourself. Yes? Yes? Okay. So people, let me know in the chat box if you guys are super duper excited for this session. Let me see the Josh of the session. Let me know in the chat box with the thumbs up if you guys are super duper excited for this session. Yes? Let me see some Josh first, then I'll be starting the session. Okay. Sai Karthik, good evening. It's okay. I didn't start the session yet. Kirito is always excited. Saurabh is always excited. Fida is always excited. Kajal, thumbs up. Yeah. Navneet is super duper excited. Yeah, Navneet, let's rock it. Yeah. Okay. Hi, Syed. How are you doing? All right. So everyone over here is super duper excited for this session. That's great. Hi, Bazilla. How are you? So people, let's get started with something called as polytropic process. Yes, what this polytropic process is all about. Let me first of all read its definition. Very simple thing. The process which follows the equation PV to the power X is equal to constant. Any process which follows the equation PV to the power X is equal to constant is what I'll be calling as the polytropic process. Now, what do we mean by that? First of all, guys, if you remember, we are done with 4 different processes. We are done with isobaric process. I've given you the idea about isochoric process, isothermal process, and adiabatic processes in detail. Yes? If you remember, for the isobaric process, the pressure of the system, the pressure of the ideal gas was kept constant. Yes? Pressure was kept constant in case of which process? In case of isobaric process. Yes, pressure of the system, pressure of the ideal gas was kept constant, was kept fixed in case of isobaric process. Yes, number 1. Number 2, in case of your isothermal processes, temperature of the ideal gas was kept constant, and your isothermal processes, they used to follow this equation. If you remember, PV is equal to constant. This is what we call as equation of state for isothermal process, if you remember. Yes, so I will call the process as isothermal, right? Okay, so all your isothermal processes, they follow this equation. PV is equal to constant. Yes, isothermal process, absolutely. Similarly, guys, adiabatic processes we have discussed, and your adiabatic processes, they follow this equation. PV to the power gamma is equal to constant, which is what we call as equation of state for reversible adiabatic process. Yes, so if the process follows this equation, then I'll be calling it as adiabatic process. Yes, and people, as we have discussed, if for any process volume is kept constant, I can call that process as isochoric process. I hope you remember all this. Yes, this is something which we have discussed till now. Now, first of all, I told you any process which follows this equation, PV to the power X is equal to constant, that's what I'll be calling as the polytropic process. Okay, first of all, people, if I'll put the value of X as 0, V to the power 0 becomes 1, so P is equal to constant. Yes, so if I'll put the value of X is equal to 0, as 0, then pressure becomes constant. That means I'm talking about the isobaric process. Yes, now people, if I put the value of X as 1, what do I get? I will get P multiplied by V is equal to constant. That means I'm talking about the isothermal process. Yes, very simple. Now similarly, if I'll put the value of x as gamma, what I'll be getting? I'll be getting PV to the power gamma is equal to constant. That means I'm talking about adiabatic process. Now at the same time, let me tell you, this equation can be also written in another form as well. P to the power 1 by x multiplied by V is equal to constant. This is how we can write this equation in a different form. Now people, if I'll put the value of x as infinity, so 1 by infinity becomes 0, P to the power 0 becomes 1, so the equation becomes V is equal to constant, and any process in which V is equal to constant, I'll be calling that process isochoric process. So I would say if the value of x approaches towards infinity, I would call the process as the isochoric process, correct? Very, very simple thing. Now this is the general equation from which I'm deriving all these equations for different processes. First of all, I put the value of x as 0, I got the isobaric process. I'm putting the value of x as 1, that means I'm talking about isothermal process. I'm putting the value of x as gamma, I'm getting the adiabatic process, and I'm putting the value of x as infinity, I'm getting the isochoric process. Now, any process in which the value of x is anything apart from these four values, any process in which the value of x will be anything apart from these four values are what we call as polytropic processes. Yes, for example, the value of x is 2, the value of x is 3, the value of x is -1, the value of x is -2, all those processes for which the value of x will be anything apart from these four values, I'll be calling those as polytropic processes. Very, very, very simple. Yes, exactly, apart from these values. Yeah. So I hope you got the clear-cut idea of what these polytropic processes are all about. Let me know in the chat box if it's clear to you. Let me know in the chat box if it's clear to you so that I can move ahead and talk about few more interesting and fascinating things about these polytropic processes. Yes? Wonderful, guys. Wonderful, wonderful. Okay, fine, great. So now let's move on and let's focus on this equation. PV to the power x is equal to constant, right? The value of x can be anything apart from the four values which I've shown you over here. Then only I'll be calling the process as the polytropic process. Yes? Now, how do we calculate work in these polytropic processes? See guys, I have shown you how do we calculate work in isothermal processes, adiabatic processes, isobaric processes, right? Similarly, how do we calculate work in these polytropic processes? That's what we have to discuss right now, okay? So let's move on and let's see how work can be calculated in these polytropic processes. Yes? Understand, guys. First of all, I'm taking a container right here. This is my container. And in this container, I'm keeping an ideal gas, which is my system, right? This is the ideal gas present in the container, and this ideal gas is my system, correct? Let's say the piston is right now at point A. When the piston is at point A, let's say volume of gas is V1, let's say temperature of this gas is T1, let's say pressure of this gas is P1, let's say moles of this gas is N, correct? Okay, now people, let's say the piston is going outwards. The piston is going outwards and piston stopped at point B finally. What happened? Volume of the container increased. Volume of the container increased. Yes, that means volume of the gas also increased. Absolutely, because ideal gas occupies the volume of the container. Absolutely, we know that. So when the piston moves from point A to B and when the piston stops at point B, let's say at that time, volume of the gas is V2, temperature of the gas is T2, pressure of the gas is P2, number of moles are still N, correct? When the piston was at point A, I will say the gas was present at the initial state at which these are the state parameters. Yes, when the piston reached at point B, I'll say the gas reached at its final state where its state parameters are V2, T2, P2 and N. Absolutely. Now people, right now what is happening? Expansion is happening and I'm assuming this process as the polytropic process. I'm assuming this expansion as the polytropic, okay? Let's assume this expansion as the polytropic. Let's call this process as the polytropic process, okay? So if it is a polytropic process, then the gas in the container, it should follow the equation. What is my general equation? My general equation is PV to the power x is equal to constant. Yes, this is my general equation. Now people, first thing, When this expansion is happening, volume of the gas is changing, at the same time pressure of the gas is changing. Yes, when the piston will be going outwards, volume of the gas will be changing, and at the same time pressure of the gas will be also changing. Absolutely. Now, how do I calculate work? I'll be simply calculating work over here as minus integral from V1 to V2. This will be P multiplied by dV, where P is the pressure of the gas. Yes. Now people understand. Can I eliminate the value of P from here? Can I write P is equal to K divided by V to the power X, or I can write it P is equal to K multiplied by V to the power minus X? Absolutely I can write it. Absolutely I can write it. So instead of this P, can I write it like this, minus integral from V1 to V2? Instead of P, I'll be simply writing as K multiplied by V to the power minus X multiplied by dV. Absolutely I can do that. What is this K? K is the constant. I can take this constant out. Absolutely, yes. So if I'll take the constant out, it becomes minus K. Now I'm going to do integral from V1 to V2. This is going to be V to the power minus X multiplied by dV. Now I'm doing the integration with respect to V. Yes, with respect to V, I'm doing the integration. After doing the integration, what will I get? I'll simply get W equal to minus K. Integral of V to the power minus X. Isn't it going to be V to the power minus X plus 1 divided by minus X plus 1 under the limits V1 to V2? Yes, I can say that. Absolutely. Now guys, see, W will be equal to minus K divided by, this is minus X plus 1. I can write it as a 1 minus X. Give the upper limit, give the lower limit. What all things I'll be getting? I'll be getting V to the power, upper limit is first of all V2 to the power minus X plus 1 minus lower limit is V1 to the power minus X plus 1. This is something which I got right now. Yes, absolutely I got it. Now. See guys, if I'll write this equation, P is equal to KV to the power minus X. If I'm writing this equation for the gas which is present at the initial state, what I'll be getting? I'll be getting, instead of P, I'll be writing P1. Instead of P, I'll be writing P1 is equal to K multiplied by, instead of V, I'll be writing V1 to the power minus X. I'm going to write the same equation for the same gas which is at final state. At that time, instead of P, I'm going to write P2 is equal to K multiplied by V2 to the power minus X. This is something which I got right now. Let me erase all this so that I get some space to do the further calculation. Yes, I am erasing all this. Now see what I'm going to do. See guys, I'm going to write W is equal to, see, this will be K divided by, I can write it as X minus 1, correct? This is minus here, okay? I did the reverse, so it will be K divided by X minus 1, correct? Multiplied by V to the power minus X plus 1. Can I write it like this? V2 to the power minus X multiplied by V2 to the power 1. Bases are same, powers will be added again. Minus. This is V1. I can write it as V1 to the power minus X multiplied by V. Can I do it? Absolutely, I can do it. Now people understand one more thing. W will be equal to K multiplied by V2 to the power minus X. K multiplied by V2 to the power minus X. Do we call that as P2? So it's going to be P2, K multiplied by V2 to the power minus X. This will be P2 multiplied by V2 minus K multiplied by V1 to the power minus X. That's going to be P1 multiplied by, this is V1, right? This is V1 divided by X minus 1. This is the simple formula which you guys are going to remember from now onwards in order to calculate the work in case of the polytropic processes. Remember guys, this is the formula which you guys are going to remember. In order to calculate the work in case of the polytropic process, I want you guys to remember this formula, which is P2V2 minus P1V1 divided by X minus 1. What is this X? X is the power of this volume right here. That's it. Yes? Let me know in the chat box if it's clear. So that I can talk about few more interesting things. Let me know in the chat box fast if it's clear to everyone. Yes, I'm going to give you the problems in some time, okay? Let me first of all make everything clear to you. Let me first of all go through the theory part once. Let me do the derivations once. Then we'll do the problems at the end, okay? And I have got some good problems to discuss with you in the today's session. Exactly, now Nate, you're correct, you're correct. P2V2 minus P1V1 divided by x minus 1, absolutely. Okay, so let's move on to one more important topic, guys. Let's move on to one more important topic over here, from which again the question frequently comes, that is calculation of molar heat capacity for any process. If we are supposed to calculate molar heat capacity for any process, how do we calculate that? In the beginning, when I started the thermodynamics chapter, in the second session, I guess, in the second session, I gave you the idea about the heat capacities, in which we talked about the, heat capacity, then we talked about the molar heat capacity, then we talked about the specific heat capacity, correct? Then we talked about the molar heat capacity at constant volume, at constant pressure. I gave you all those relations, if you remember, right? I gave you all those relations, and at the end we did some questions as well. Now it's the high time to talk about this molar heat capacity in detail. Yes, exactly, Kirito, where I gave you a chart. Yes, you remember, wonderful. Yes, Saurav, we can write the same equation in terms of temperature as well. It's completely your wish. Yeah, absolutely. You can do that. Okay, I'm moving on, and let's talk about the calculation of molar heat capacity for any process. Yes, calculation of molar heat capacity for any process. Okay, so people, follow me what I'll be doing now. You're going to follow me from now onwards. See, guys, what I'm going to do. First of all, how do we define the molar heat capacity? Molar heat capacity of the ideal gas I'm talking about, right? I'm talking about the molar heat capacity of the ideal gas. If you remember, molar heat capacity used to be equal heat capacity per unit mole, C divided by N, if you remember. Yes, this is how we used to define the molar heat capacity. Correct? Very simple. And C, guys, C is the heat capacity. If you remember, I told you in the earlier session, C is equal to dQ divided by dt. So it becomes dQ divided by N dt. Yes? Yes, very simple. So can I say Cm? So what is Cm? Cm is molar heat capacity, which is going to be dQ divided by N dt. For example, in the container, I have got 1 mole of ideal gas. Let's say in the container, I have got 1 mole of ideal gas. Can I say N value for that ideal gas is going to be 1 if I'll be having 1 mole of ideal gas? So Cm is going to come as dQ divided by dt. Yes, I can write it. Now people, if you remember your first law of thermodynamics, what was first law of thermodynamics? du is equal to dq plus dw. Yes, do you remember this? Right? Do you remember this? Absolutely. So from this equation, can I get the dq value, which is going to be du minus dw? Yes. Now what I'm going to do, I'm going to replace this dq right here. It becomes du minus dw divided by dt. Yes, I can do that. I can do that. Absolutely. Absolutely, I can do that. Now, people, Cm will be equal. This is du. What is du? Small change in internal energy for 1 mole of ideal gas. Du, as you all must be knowing, du is equal to NCV dt. Yes, for n moles of ideal gas. But right now, I have already taken 1 mole of ideal gas, so n value will be equal to 1. So du will be equal to Cv dt. Very, very simple. So instead of du, I'll be writing Cv and dt minus dw. dw is pdv. Yes, minus pdv if you remember. dw, small amount of work. dw minus pdv. So it becomes plus pdv divided by dt. Over here, I'm doing the division by dt. Over here, I'm doing the division by dt. This dt and this dt got cancelled. So I got the formula Cm, molar heat capacity for 1 mole of the ideal gas. It will be simply equal to Cv. What is Cv? Cv is the molar heat capacity of the ideal gas at constant volume plus P multiplied by dV upon dt. Correct? This is one relation, but you're not supposed to remember this relation. You're not supposed to remember this relation. I'm going to use this relation. And how I'll be using this relation? For that, I need to do few more calculations right here. See, guys. See, very, very simple. First of all, just now we saw one equation. What was that? PV to the power x is equal to constant. This was one equation which we discussed few minutes back. Yes. PV to the power x is equal to constant. Now people, since in the container, I have taken the ideal gas, which is my system right now, and I have taken 1 mole of ideal gas. Yes. Yes. Now. See guys, for ideal gas, it has to follow this equation, PV is equal to nRT. Since number of moles of ideal gas I have taken in the container as 1, so PV will be simply equal to RT. Yes, I can do that. Now people, I can write it like this. P is equal to RT divided by V, or I can say P is directly proportional to T and inversely proportional to V because R is a constant. I can say that, absolutely. Now, instead of this P, I can simply put T by V in this equation. So I'll be getting T divided by V multiplied by V to the power X is equal to constant. Can I do this? Absolutely, I can do this. Absolutely, I can do this. Okay, I'm erasing this part. I'm erasing this part. Now, what equation I'll be getting? I'll be getting T V to the power X minus 1 is equal to constant. This is something which I got. This is something which I got. Either you write the equation in the form of PV to the power X is equal to constant, or you can write it in the form of temperature and volume, and it becomes TV to the power X minus 1 is equal to constant. Yes? Yes? Now. Since we have to calculate this value, dV upon dt. We have to calculate this value, dV upon dt. Okay? And after getting the dV upon dt, I'm going to put that dV upon dt value into this equation. I'll get the final result. Yes? Now. In order to calculate dV by dt, I'm going to differentiate this equation throughout by temperature, with respect to temperature. I'm going to differentiate this equation throughout with respect to temperature because I need to get the value of dV by dt, right? So only method that's left to me is I'll do the differentiation with respect to temperature, yeah? So what I'm going to do, I'm going to write d upon dt of this thing, of this equation will be equal to d upon dt of constant. D upon dt of constant will be 0, yes? Simply I'm writing d upon dt of constant will be simply 0. Yes? Now, understand. Now I'm going to use the simple UV rule, as you all must be knowing, all of you are math students, yes? So I'll keep the temperature as such. I'm going to differentiate this term V to the power X minus 1. I'm going to differentiate it, right? And I'm differentiating it with respect to temperature. So it becomes X minus 1 V to the power X minus 2 multiplied by dV upon dt. Yes? I have kept the temperature as such. UV rule I'm using, UV rule. I have kept the temperature as such. I have done the differentiation of V to the power X minus 1, right? And X to the power N differentiation is NX N minus 1. That's what we do, yes? So I did the differentiation V to the power X minus 2 and it becomes dV upon dt. Now I'm going to keep the V to the power X minus 1 as such. I'll do the differentiation of temperature. dt upon dt is 1. So it becomes simply 1 is equal to 0. Yes? I got something like this, absolutely. Now people, understand one more thing. I'm going to write T multiplied by X minus 1 multiplied by V to the power X minus 2 into dV upon dt is going to be equal to what? It's going to be equal to minus times V to the power X minus 1. This is something I can write. This is something I can write. Absolutely. Now people, if I take this V raised power X minus 2 into the denominator, V to the power X minus 2, over here I'm taking the denominator, right? So I'm going to erase this V to the power X minus 2 from here. Yes, I erase this, correct? I erase this. So what I'll be getting? I'll be getting T multiplied by X minus 1 into dV upon dt. This will be equal. Bases are same, powers are subtracted in case of division. So this becomes V to the power X minus 1 minus X plus 2. Yes, normal mathematics I'm doing. Normal calculation part I'm doing. Yes. So what I'll be getting from here? I'll be getting something like this. I'll be getting something like this. T multiplied by X minus 1 multiplied by dV upon dt. dV upon dt will be equal to minus times V, right? This X minus X and this X got cancelled. 2 minus 1 is 1. So V to the power 1. Very simple. Now people, I got the dV by dt value which I was supposed to calculate. dV by dt value is nothing. It is just minus V divided by T multiplied by X minus 1, right? Very simple. Or I can write it further like this. dV upon dt is equal, if I take minus common in the denominator, it becomes V divided by T multiplied by 1 minus X. Now I got what I was supposed to calculate, dV by dt value. Now what I'm going to simply do is I'm going to put the value of dV by dt into this equation. I'll be getting the final result. I'll be getting the final result. And final result which I'll be getting, for that I need some space right here. Let me erase this part. I hope you have copied it, right? Now, see what I'm going to do. I'm going to write molar heat capacity for the ideal gas will be equal to CV plus P multiplied by dV by dt value. We got to know that is V divided by T. That is V divided by T multiplied by 1 minus X, right? Now people, as per the ideal gas equation is concerned, PV is equal to nRT, right? N value is 1 because I'm talking about 1 mole of ideal gas. So PV is equal to RT for 1 mole of ideal gas. If PV is equal to RT, Can I say PV divided by T will be equal to R? Right? For 1 mole of ideal gas. For 1 mole of ideal gas, PV is equal to RT. So I would say R will be equal to PV by T. So I'll be getting the final result as CM is equal to CV. Instead of this PV by T, I'm going to write R. Just a second, guys. Just a second. Let me erase this part. I'm going to write R divided by 1 minus X. This is one result which I'll be directly using in the problems. Correct? This is how we calculate molar heat capacity for 1 mole of ideal gas. Correct? Cm is equal to Cv plus R divided by 1 minus X. Correct? Let me know in the chat box if it is clear to you. Let me know in the chat box if it is clear to you, so that I can move ahead and I can give you some good questions over here by means of which you'll understand the concepts properly. Let me know in the chat box fast. Yes? Is it clear to everyone? Is it clear to everyone? Let me know in the chat box fast. Now, first of all, you should know how this formula comes, how this formula is coming. That's why I'm giving you the derivation as well, right? Because it makes things easy. Okay, so this is how I'll be calculating the molar heat capacity for any process. Okay, now people, how to use this equation, that is the point. Yeah, I will be giving you certain questions by means of which most of your concepts will get clear right here, and you'll get to know how to use this sort of equation. Yeah, okay, I'm moving on to the questions. And the first question is on your screen. Have a look, guys. Calculate the molar heat capacity of a monoatomic gas for which the ratio of pressure and volume is 1. These are all the asked questions in JEE, okay? Whatever questions I'm going to take now, all these questions have been asked in your mains, right? Okay, calculate the molar heat capacity of a monoatomic gas for which the ratio of pressure and volume is 1. So first of all, I'm given with a monoatomic gas. Now people, regarding monoatomic gas, I know few things. Regarding monoatomic gas, we know CV value for monoatomic gas is simply 3 divided by 2R. Do you remember this? Absolutely, we know it, correct? What are we supposed to calculate? We are supposed to calculate the molar heat capacity. And molar heat capacity, all of you must be knowing, that is equal to R plus, I'm going to write it like this. That's equal to CV plus R divided by 1 minus X, right? This is how we calculate molar heat capacity, correct? Now, the point is, how do we get this X? It's a very simple question. How do we get this X? For that, something is given in the equation. The ratio of pressure and volume is 1. Yes. So can I say PV to the power minus 1 is equal to 1? Yes. PV to the power minus 1 is equal to 1. Can I say, guys, this equation is resembling with some equation which we discussed right now? Can I say this equation is resembling with PV to the power X is equal to constant, right? If this equation is resembling with the equation which we discussed few minutes back, you can directly say the value of X over here. Can I say I got the value of X as minus 1 right here? Yes, I got the value of X as minus 1. The equation which I'm given within the equation, it is resembling with my polytropic equation, so I can conclude the value of X as minus 1 from here. Yes, very simple thing. Very simple thing. Yes. Now, I'm going to write it like this. Cm will be equal to Cv plus R divided by 1 minus X. What is the value of X? Value of X is minus 1. So it's going to be equal to Cv. Cv value already we know, that is 3 divided by 2R plus R divided by 1 plus 1 is 2. So you got the molar heat capacity value which we were supposed to calculate, which is going to be 3R plus R, 4R. 4R divided by 2 means 2R. This is the value of molar heat capacity which we were supposed to calculate. Very simple. Yes. Let me know in the chat box if it's clear. Let me know in the chat box if it's clear fast. Let me know in the chat box if it's clear. Fast. Yes, give me the thumbs ups. I'm sure you got the concept. Yes. Yes, all clear. Wonderful. All clear. That's great. I'm moving on to one more question then. Let me see if you can solve that question or not. Okay. I am moving on to one more question. Let me see if you can solve this or not. Again, the question have been asked in your JEE, okay? The molar heat capacity of a gas for which P and V are equal, pressure and volume are equal, is 7R by 2, okay? What will be the nature of the gas? What will be the nature of the gas? Is the gas going to be monoatomic? Is the gas going to be diatomic? Is the gas going to be polyatomic, non-linear, or none of the above? Yes? So basically we have to check the nature of the gas. How do I check the nature of the gas? People, do you remember? If you know the gamma value for a gas, you can tell the gas whether it is monoatomic, diatomic, polyatomic, linear, or something. Correct? Now, how do we get the value of gamma? Okay, gamma value we can get only by Cp by Cv. Yes, that's how I can get the gamma value. Yes, but people, if you will just know the Cv value for the gas, let's say I am getting the Cv value from this question as 3 by 2R. That means the gas will be monoatomic. If I am getting the Cv value as 5 divided by 2R, that means the gas is diatomic or triatomic linear. Or if I'll be getting the Cv value as 3R, that means the gas is polyatomic non-linear. Yes, I have given you that table by means of which we could recognize. Yes, Yogesh is saying it's polyatomic. Yogesh, let's try it. Let's check. I have no idea whether the gas is polyatomic or something. Let's check it. First of all, the molar heat capacity of a gas for which P and V are equal is 7R by 2. So first of all, I'm given with the value of Cm, molar heat capacity of the gas, which is 7R divided by 2. Yes, this is something which is given to me. And I'm given with one more parameter, pressure and volume are equal. If P and V for the gas are equal, can I write it like this? P divided by V is equal to 1. Can I write it further like this? PV to the power minus 1 is equal to 1. Can I say this equation is resembling with my equation, which is PV to the power x is equal to constant? So can I get the value of x from here, which is minus 1? So I got the value of x from here as minus 1. Yes, I got the value of x. Molar heat capacity, you know the formula, guys. Just now we have discussed that. That is Cv plus R divided by 1 minus x is equal to 7 divided by 2R. Absolutely. Yes. So Cv plus R divided by 1 minus x. So this is 1 minus x is minus 1. So it's 1 plus 1, 2 is equal to what? 7 divided by 2R. The equation is done. So Cv value will be 7 divided by 2R minus R divided by 2. So you are getting the Cv value as 3R. Now people, if you remember the chart which I have given you, we got the Cv value for the gas as 3R. For which gas Cv value is 3R? Tell me that. For which gas Cv value is 3R? Do you remember? In case of polyatomic non-linear gases, Cv value is equal to 3R, Cp value is equal to 4R, and gamma value is equal to 4 divided by 3 for the polyatomic non-linear gases. Do you remember that? So I got to know simply that Cv value is coming as 3R. So the gas must be polyatomic non-linear. Yes? Let me know in the chat box if it's clear. Fast, so that I can move on to a few more questions. Yes? Absolutely. Wonderful, guys. Wonderful. Let's move on to one more question and let me see if you can solve this or not. Calculate the amount of heat supplied to raise the temperature of 5 moles of a gas by 50 degrees centigrade. The ratio of pressure and volume is 2. Okay, guys, let me tell you, you can modify the question a bit because it's incomplete. 5 moles of, you write it as 5 moles of monoatomic gas. Okay, 5 moles of monoatomic gas. Now you try it out. Okay, now you try it out. Calculate the amount of heat supplied to raise the temperature of 5 moles of monoatomic gas by 50 degrees centigrade. The ratio of pressure and volume is 2. Yes, this is something which we have to calculate. I'm sure all of you can solve this question now. First of all, if you remember, I told you, I have given you one flow chart, if you remember, long back in this chapter itself, right? We can calculate the value of Q in certain ways, if you remember. If heat capacity is given, if specific heat capacity is given, if molar heat capacity is given. If heat capacity of a substance is given, then how do we calculate heat exchange between system and surroundings? It is simply C delta T. If specific heat capacity of the gas is given, of the system is given, then how do I calculate Q? Q I'll be calculating as MS delta T, right? And if Cm is given, molar heat capacity of the gas is given, then how do I calculate heat exchange between system and surroundings? It becomes NCm delta T. So basically over here, I am going to use this relation in order to calculate the heat, the amount of heat supplied. In order to calculate the amount of heat supplied, okay, I'm going to use this relation, correct? I'm going to use this relation. Yes, yes. Why I'm using this relation? Because I can easily calculate Cm value for the gas. Because I can easily calculate molar heat capacity value of the gas. Yes, for which the formula I have given you a few minutes back. Okay, let's try it out and let's get the answer. First of all, let's try to calculate the molar heat capacity, which will be equal to Cv plus R divided by 1 minus X. Yes. Now Cm, that is the molar heat capacity of the monoatomic gas, will be equal to Cv value for the monoatomic gas, as you all must be knowing, that is 3 divided by 2R plus R divided by 1 minus. Now I do not know the value of X. Yes, but the ratio of pressure and volume is 2. The ratio of pressure and volume is 2. So I can write it like this, PV to the power minus 1 is 2. Can I say this equation is resembling with PV to the power X is equal to constant? So I'm getting the value of X as minus 1 over here also. Yes, I got the value of X as minus 1. Correct? Now people, I got the Cm value. I got the molar heat capacity for the gas. That is 3 by 2R plus R divided by 2. This will be how much? This will be 4R divided by 2 means 2R. I got the molar heat capacity of the gas. Since I got the molar heat capacity of the gas, in order to calculate how much heat is supplied, to raise the temperature of 5 moles of the gas by 50 degrees centigrade, I'll be simply using the formula Q is equal to N Cm delta T, right? And Q will be equal to N value, number of moles of the gas, that is given to me as 5 moles. Cm, molar heat capacity of the gas, I got to know as 2R, right? Delta T, change in temperature. How much is the change in temperature? The temperature of the gas has increased by 50 degree, right? So 50 units is the change in temperature. Yes, so delta T is 50, correct? Just get the value of Q from here. This is 5 2s are 10. This will be 500 R. Very simple. So this much heat energy is absorbed by 5 moles of the gas. Then only its temperature will be increased by 50 degrees centigrade. Ankit, the Menti syllabus is going to be electrochemistry. I'm going to have the Menti quiz from the chapter electrochemistry, okay? On Saturday at 1 p.m. Yeah. Absolutely, Chinmay. Narendra Avasthi is like very good book for physical chemistry. Exactly. Saurabh, this is the change in temperature. If you calculate the change in temperature in Kelvin or degree centigrade, it's going to be same. For example, I have got the system which is at 5 degrees centigrade. Now I'm increasing its temperature from 5 degree to 10 degrees centigrade. What is the change in temperature? Change in temperature is 5 units. Yes. Now 5 degrees centigrade means 278 Kelvin. 10 degrees centigrade means 283 Kelvin. Still the change is 5 units, right? If you want to calculate the change in degree centigrade or change in Kelvin, it's going to be same, yeah? Absolutely, Dinesh. This is one of the scoring topics from your JEE. Yes? So remember it. Got it? Okay. Let me give you one more question then. Let me see if you can solve that or not. Okay. I hope this question is done. This is clear to everyone. So just a second. Let me see if you can solve one more question or not. Okay. People, this is one last question of the today's session, and with this I'll be taking a leave. Okay. With this I'll be taking a leave, and with this your polytropic processes and molar heat capacity will be done. Okay. So people, do it. I'll be waiting for your answers. Write the answer in the chat box fast. Do it. Give it a try. Very simple question it is. For 1 mole of monoatomic ideal gas, during any process, T square is equal to kV to the power 3. Calculate molar heat capacity during the process. Yes? Very simple question. Give it a try. Let me know the answer in the chat box fast. Hi Snehal, how are you doing? Ankit, lecture 7 of electrochemistry is already there, I think. Yes? Dinesh, this topic is not that much important for NEET, okay? For JEE, it's important. Yogesh, it's your wish. We were in the earlier question, we were talking about change in temperature. Whether you want to whether you want to take the change in temperature in Kelvin or degree cent, that's going to be same, yeah? I told you that. Right? Ankit is saying it is done. Ankit, let me know the answer in the chat box then. Let me know the answer in the chat box if it's done. Let me know the answer in the chat box fast. Okay. All right. So let me try it out. Let me try this question out. For 1 mole of monoatomic ideal gas. So monoatomic ideal gas means CV value for the gas is how much? 3 divided by 2R. Yes, this is the CV value for the gas. During any process, T square is equal to kV cube. What is given to us? We are given with the relation T square is equal to kV to the power 3. This is something which is given to me. Calculate the molar heat capacity during the process. We have to calculate molar heat capacity. Yes. Now. Since we are talking about the ideal gas. People, my equation was, I guess, PV to the power minus X is equal to constant. Okay. Is this relation resembling with this relation? No, it's not. Let's try to convert this relation into this form. Yes. Let's try to convert this relation into the form which we know. How do we do that? Since we have got the ideal gas, right, in the container, we have got the ideal gas, and for ideal gas we know PV is equal to nRT, yes, or I can say T will be equal to PV divided by nR, or can I simply say temperature is directly proportional to pressure as well as volume. Temperature is directly proportional to pressure as well as volume. Yes, because the number of moles of the gas is fixed, R value is fixed, so I can say temperature is directly proportional to pressure as well as volume of the gas. Yes, so instead of temperature of the gas, can I write PV to the power whole square is equal to KV to the power 3. I can write it like this, absolutely. Yes, I can do that. I can do that easily because the system is the ideal gas. Now, can I write it like this? P square V square is equal to KV to the power 3. Correct? So people, this will be P square V square divided by V to the power 3 is equal to constant. So can I be writing it like this? P square, this will be V square and square will be cancelled, so V will come up. P square V to the power minus 1 will be constant, correct? Still the equation is not resembling with my equation, PV to the power X is constant, yeah? So what to do? I'll be taking the root on both the sides. So this will be P square raised power 1 by 2, V to the power minus 1 raised power 1 by 2 will be equal to square root of constant, that will be one more constant, yes? Yes, very simple. Now people, this two got cancelled. So this is P, V to the power minus 1 by 2. This is coming as constant. Now people, I have converted the relation into the equation which I already know. PV to the power X is equal to constant. Yes, PV to the power X is constant. So what I got to know? I got to know the value of X is equal to minus 1 by 2. The equation is done and dusted. Yes. X value I got to know as minus 1 by 2. X value I got to know as minus 1 by 2. Correct? So I'll be using the formula Cm, molar heat capacity of the ideal gas. That's going to be Cv plus R divided by 1 minus X, if you remember. What are we supposed to calculate? Cm we are supposed to calculate. So Cm, molar heat capacity, will be equal to Cv value. Cv for monoatomic gas is 3 divided by 2R plus R divided by 1 minus X. X value we got to know as minus 1 by 2. Yes, this is something which we got. Now, it will be 3 divided by 2R plus R divided by, this is 1 plus 1 by 2, that means 3 divided by 2, so this becomes 2R divided by 3. Yes, now just solve it. This is 3 3s are 9R, 9R plus 4R means 13R, so 13R divided by 9 will be the value of molar heat capacity for the gas which we were supposed to calculate. Yes, sorry, it's not 9, it's 3, yes, it's 6, I mean. 3 2s are 6, yeah. This is the value of molar heat capacity which we'll be getting right here. Let me know in the chat box if all the concepts are clear to you. Let me know in the chat box if all the concepts are clear to you fast. Yes. So people, with this, I'm concluding today's session. Okay, I hope you would have enjoyed the session. The session was short, crisp, and to the point. I'm sure you can solve all these type of questions from now onwards. Okay. Now, for the ones who joined us late, let me tell you, we have started one JEE 2021 crash course on the actual Vedantu platform. We are going to cover everything before your JEE 2021. Okay, which includes your syllabus completion, which includes the regular test series and the mock tests. We are going to train you personally for your physics, chemistry, as well as mathematics, right? If you want to get trained properly, personally by the master teachers of Vedantu, so do join this crash course. And how do we join this crash course? There's a link in the description description box. Click on that link. Use the coupon code as WSCC for the particular crash course for the people who are going to appear in the JEE 2021. Okay, you are going to get the discount of 30% if you are using this coupon code of WSCC. Okay, so people, this is the link in the description box. Click on the link, use the coupon code as WSCC. You guys are going to get the 30% off on this. Yes, yes. Okay, so there is one more link in the description box. Click on that link as well, which is for the Telegram. So click on that link, get added to the Telegram group, right? So stay updated about the classes as well, correct? And at the end, please do like the video, share and subscribe at the same time so that everyone will get benefited out of these sessions. Okay, so this was all from my side for today, guys. Okay, tomorrow I'll be meeting you at same 5:30, and tomorrow again we are going to do one of the important topics as per your JEE is concerned from the chapter Thermodynamics. That's going to be your free expansion and the cyclic processes. Both the things are really very important. Yes, yes. बाबर, मैं नीट एलीट पे आज रात को 11 बजे आऊंगा. I have changed the timing of the NEET Elite. Okay, on NEET Elite I'll be coming live tonight at 11 p.m. Okay, so you can watch me at 11 p.m. Let's try it out how the night session will go. Let's try it out. I hope it will be fun to teach in the night. Yeah. So I'll see you guys tomorrow at 5:30. Till then, you guys take care. Bye bye. God bless you all and love you all. Take care, guys. Bye.